Let's look at the solutions of quality quant questions, week 27. A 4-digit number is formed using the digits 0, 2, 4, 6, 8 without repeating any of them. What is the sum of all such possible numbers? Okay. Now we have to create a 4-digit number using these 5 digits. What we can potentially do is, let's list out all combinations of 4 digits. The first combination would be 0, 2, 4, and 6. The next combination will be 0, 2, 4, and 8. Next combination will be 0, 2, 6, and 8. Then 0, 4, 6, and 8. And the last one will be 2, 4, 6, and 8. Of these combinations, this is the easiest to handle. 2, 4, 6, 8 because 0 is not present. So for this, the formula for solving this question, when no zeros are involved, is number of digits factorial, 4 factorial by 4, because 4 digits are present. This gives us the number of times each digit comes in that 4-digit number into sum of all the digits, which is 2 plus 4, 6, 6 plus 6 is 12, 12 plus 8 is 20, into 20, into 1111 as many times as the digit number that you are creating. I'm creating a 4-digit number. So this is what I'll get. Or to simplify it, we'll get 6 into 20 into 1111. Now this formula works, this expression works when you have no zeros involved. If 0 is involved, why this doesn't work is, then you can also potentially have 0 in the leading place. Because 0 can be in the leading place, it will no longer be a 4-digit number. So in order to overcome that, what needs to be done is, first you solve it precisely this way, and then you solve it precisely this way, which will get you to 6, 4 factorial by 4, and directly writing 6 by into sum of the digits, which is 2 plus 4 plus 6, 12 into 1111. And then you subtract sum of all 3-digit numbers that can be made using these 3 digits, 2, 4, and 6. That will be 3 factorial by 3. So 2 into, again, sum of digits 12 into 111. And we'll get the sum here. In the same way, we'll do it for the second group also. 6 into 14 into 1111 minus 2 into 14 into 111. Same way we'll do it for the next group and the next group. 6 into 16 into 1111 minus 2 into 16 into 111. And finally, we'll have 6 into 18 into 1111 minus 2 into 18 into 111. And now our trusty calculator will come to our aid. Before that, we can potentially take out 2 into 12 common. And we'll be left with 3 into 1111. So 3, 3, 3, 3 minus 111 or 3 triple 2. So 2 into 12 into 3 triple 2. Now see, processing wise, from this expression to this expression, we can do the same thing. 2 into 14 comes out common. And we'll be left with 3 into 1111 minus 111 into 3 triple 2. Here also 6 into, sorry, not 6, 2 into 16 into 3 triple 2. And here 2 into 18 into 3 triple 2. Now from these, I can take 12 plus 14 is 26, 26 plus 16. 26 plus 16 is 42, 42 plus 18 is 16. So these 4 can be combined to 2 into 60 into 3 triple 2. Remember, this is summation for these 4. And I also have a 6 into 20 into 111. Now 6 into 20 is 120. 2 into 60 is 120. So I have 1. When I add these 2 up, I'll have 120 in common. I'll have 3 triple 2 plus 1111 or 120 into 4333. And now this final multiplication, we can use our calculator. Sorry, there is one more 3. 1, 2, 3, 4 into 120. Our final answer will turn out to be 519960. This will be the answer to this question. Now, these sorts of questions where sum of digits is needed from however many numbers you can create. This is very common in NMAT. So if anyone has this exam coming up, please make sure this concept, this processing, basic processing, you are familiar with. Okay. Next question. The question paper consists of 5 problems, each problem having 3 internal choices. In how many ways can a candidate attempt one or more problems? Okay. For question 1, let's say the 3 internal choices were A, B, and C. For question 1, the candidate can mark it, the answer as A, or B, or C, or choose to skip it. There is no compulsion that you have to attempt all questions. So for question 1, he can attempt it in 4 ways. And question 1 is no more special than question 2. If question 1 can be attempted in 4 ways, question 2 can be attempted in 4 ways, question 3 can be attempted in 4 ways. All the questions, be it question 4 or question 5, there are 5 questions only. All questions can be attempted in 4 ways. So in how many ways can questions be attempted? It is 4 raised to the power 5. But within this, there is also going to be a case where you're skipping question 1, you're also skipping question 2, you're also skipping question 3, you're also skipping question 4, you're also skipping question 5. Basically, you attempted no questions. But the question was, in how many ways can a candidate attempt one or more? So at least one you have to attempt. So that unique case when you skipped all the questions, that has to be removed. 4 raised to the power 5 is 1024 minus 1. Our final answer will be 1023. The answer to the question is 1023. Next one then. In how many ways can 8 letters be put in 8 differently addressed envelopes such that exactly 5 letters go into the wrong envelopes? Okay. Now this is a question based around the concept of derangement. Now, first we have to select the 5 letters that go into the wrong envelopes. Those can be selected in 8C5 ways. Then, how can they go into the wrong envelopes? That will be derangement 5. Now, value of derangement 5 is 44. So, our answer is simply 8C5 into 44. Now, for derangement, the expectation is you would know derangement numbers up until 6 at least. You would know derangement numbers up until 6 at least. Derangement 7, derangement 8. See, derangement as a concept has only been tested in NMAT. And even in NMAT, the highest they have gone up to is derangement 5. So, even if you were to look to expand your knowledge of derangement, you can go ahead and learn 7 and 8 and however many numbers, but it is highly unlikely you'll get a number beyond that. So, for derangement, just to know up till derangement 6, it is going to be more than enough. D1, D2, D3, D4, D5, D6. And as long as you know up until D6, all your derangement questions will be very, very straightforward. The answer to this question is, of course, option A. First, you're selecting the 5 envelopes which have the wrong letters. And then, how can wrong letters go in those 5 envelopes so that no envelope is correct? That will be done in 44 ways. The remaining 3 letters and 3 envelopes will, of course, be right. So, nothing needs to be done there. Okay. In the figure, in how many ways can a person walk from A to C via B? If he walks either rightwards or upwards. Okay. See, from A to C, he has to go via B. So from A to B, he has to take one right movement to one right movement to one right movement. He will reach here. Then upwards, he has to go one up, one up, one up, one up. So, in order to go from A to B, doesn't matter in which order he takes the steps, he has to take 4 U's and 3 R's. 4 U's and 3 R's. And they can be rearranged in 7 factorial by 4 factorial by 3 factorial ways. which will be equal to 7 into 6 into 5 by 6, which will be equal to 35 ways. From A to B, the journey can be completed in 35 ways. Now, from B to C, again we do the same processing. 1 right, 2 right, 3 right, 1 up, 2 up. From B to C, the journey has to be completed with 3 rights and 2 U's. I have 2 U's and 3 rights. This can be done in 5 factorial by 2 factorial, 3 factorial, which will be equal to 10. This 5C2 basically. So, from A to B, you can go in 35 ways. From B to C, you can go in 10 ways. So, in how many ways can you go from A to C if you have to go via B? The answer will be 35 into 10, which is equal to 350. 350. Okay. Next question. Let n be the number of ways in which 5 men and 6 women can stand in a queue, such that all the women stand consecutively. Okay. Man, and man, and man. Man 1, man 2, man 3, man 4, man 5. These 5 men, I can make them stand. And for these 5 men, there are 6 spots where the women can come in. So, first thing I'll do is, in how many ways can I arrange these men? I can do that in n, value of n we are finding. N is equal to, men can be rearranged in 5 factorial ways. Now, where will women come? Where will women come? That spot can be selected in 6 ways, 6C1 ways or 6 ways. Then, the women, wherever they end up at, they can rearrange themselves within that group in 6 factorial ways. So, value of n is 5 factorial into 6 factorial. Now, let m be the number of ways in which the same 11 persons can stand in a queue, such that exactly 5 women stand consecutively. Exactly 5 women stand consecutively. Okay, let's look at 10. The first step is still men will stand in 5 factorial ways. But now, when we are selecting spots for women, we would have to select 2 spots. In one spot, there will be only 1 woman. There will be only 1 woman. In the other spot, there will be 5 women. So, first we have to select 2 spots, 6C2. Now, among these 2 spots, I am selecting the spot in which 1 woman comes. Among these 2 spots, I am selecting 1 spot in which 1 woman comes. The other spot is automatically allocated to the 5 women group. So, 2C1, I select a spot where 1 woman comes. Now, which woman will come? That I can select in 6C1 ways. The other spot, which was automatically selected for the 5 women, in that spot, the remaining 5 women can come in 5 factorial ways. So, m will be equal to this expression, n will be equal to this expression. Finally, they've asked us the value of m by n. So, let's try to figure out 5 factorial into 15 into 2 into 6 into 5 factorial. Whole thing divided by 5 factorial into 6 into 6 into 5 factorial. I've broken down the 6 factorial into 6 into 5 factorial so that I can cancel off these 5 factorials very easily. I can also cancel off this 6 and 6. I'll be left with 30 by 6, which is equal to 5, or option A is the right answer. Okay. Next, in a staircase, there are 4 steps. A person can take 1 step, 2 steps, 3 steps, or 4 steps. In how many ways can he reach the top? Okay. Let's say, if he takes all 4 1 steps, 0 2 steps, 0 3 steps, and 0 4 steps, he can reach the top, no problem. Next case, can he take 3 1 steps and then some combination of other steps? No, it's not possible. Let him take 2 steps here, 2 1 steps, 1 2 steps, 0 3 steps, 0 4 steps. This is very much possible. Next case, let him take 1 step here, 1 step here, 0 steps here, 0 steps here. This is very much possible. Let him take 0 steps here, 2 steps here, 0 steps here, 0 steps here. This is very much possible. 2 into 2, 4 steps are accomplished. Last case, 0 steps here, 0 steps here, 0 steps here, and one iteration of 4 steps. So this will give us the exhaustive number of steps that he can take in order to reach the top. In how many ways can he take 4 steps? All the 4 steps are identical. He can only do it in one way. In how many ways can he take 2 1 steps and 1 2 step? The 2 steps could be the first step, could be the second step, or could be the third step. So in the total number of ways in which this can be accomplished is 3 ways. In how many ways can he take 1 1 step and 1 3 step? He can do it in 2 ways. Either he takes the 1 step first or he takes the 3 steps first. Here, both the steps are identical, so this can only be done in one way. Here, there is only 1 step, so you can do it in one way. Altogether, we get 1 plus 3 plus 2 plus 1 plus 1. We can reach the top in 8 ways. Okay. Next, there are 4 married couples in a club. The number of ways of choosing a committee of 3 members such that no couple appears in the committees. Okay. First, we will select 3 married couples out of the 4. Selecting 3 married couples out of the 4, which can be done in 4C3 ways. Now, from within each couple, I have to select one person, and every couple has to be members. So I can do that in. From the first couple, I take 2C1. From the second couple, I take 1 person out of 2. From the third couple, I take 1 person out of 2. And this should give me the answer. 4C3 is 4, 2C1, 2C1, 2C1 is 2 into 2 into 2. Or altogether, we will get 32 here. The number of ways of choosing a committee of 3 members such that no couple appears in the committee is 32. Okay. Another way you could potentially have solved this is this. In how many ways can a committee be chosen without any restrictions? It would be 8C3, 4 couples, 8 people. 8C3. This is 8 into 7 into 6 by 6, which is 56. But within these, there are also going to be committees that have a couple involved. So let's say which couple is getting involved. Let's select that in 4C1 ways. Both the members are there. And from the remaining 6 members, we select one more committee member. That can be done in 6C1 ways. So you have 24 unacceptable ways. These are 24 unacceptable ways. This is what total number of ways. These are 24 unacceptable ways. Even if you take the difference, there will be 32 ways in which you can create the committee. You could solve it in either way. I prefer the first one because it is very straightforward. I don't have to do calculation twice. Next, how many distinct 5 into 5 tables are there such that each entry is either 0 or 1 and each row sum and each column sum is 4. Okay. So if I try to make a table 5 by 5 matrix per se, 1, 2, 3, 4 and 5. 1, I have 2, I have 3, I have 4 and 5. Let me try to create one such table. Because I know each column sum is 4, each row and each column sum is 4. It means in each column and each row there is going to be 1 0 and 4 1s. So let me put a 0 here and 4 1s here. Also, as soon as I place a 0 here, for this column also I need some 4. So these will also turn 1. Now, some other spot I want to put a 0. Let's say I put a 0 here. So everything in its column, everything in its row will turn 1. Now I have to put another 0 somewhere. Let me put it here. Everything in its column and everything in its row will turn 0. Sorry. This. Now, I can put another 0. I can put another 0. Now, the beauty of this question is, can you see these? The way you have to do it is, you have to place 5 zeros in such a way that no two zeros are in the same row and same column. You have to put 5 zeros in such a way that they are no longer in the same row and same column. In fact, this precise order from top to bottom is also not necessary. See how we can potentially replicate the work. If I were to add a separate row and erase the top, the first column needs a 0, second column needs a 1, 1, 1, 1. Can you remember? The first row was precisely this. The order in which these rows appear is not confirmed. The order in which these rows appear is not confirmed. So, in how many ways can we accomplish this precise task of filling up a 5 by 5 table with either 0 or 1 such that each row and each column sum is 4? It is simply these 5 rows are going to be distinct. They can come in 5 factorial ways. Therefore, there are 120 ways in which it can be done. Now, some may think they've only thought about rows. How about columns? As soon as you do the work for rows, the work for columns is done. Or as soon as you do the work for columns, maybe somebody was thinking along the lines of columns. As soon as you do the work for columns, the row work is done. You don't need to do the work in repetition. As long as you've taken care of either rows or either columns, both the pieces of work will get done instantly. Okay. Next question. India and South Africa play one-day international cricket series until one team wins 4 matches. No match ends in a draw. Find in how many ways can the series can be won. Okay. And you see India can win the series and it has 4 wins, or it has 4 wins and 1 loss, and it has 4 wins and 2 losses, or it has 4 wins and 3 losses. Now, remember, in all these, as soon as you win 4 matches, the tournament is supposed to stop. So, the last match that you played, because I'm looking for India victory, the last match played should have an India victory, because it cannot possibly be that India won the first 4 matches and the next 2 matches South Africa lost. No, cannot happen. The last match has to be won. The last match has to be won by India only for one of these cases to exist. So, in how many ways can India win 4 straight matches? 1 way. 4 straight matches. Here, in how many ways can India win? I have 4 victories and 1 loss. And also, the last win has to be India. So, among the first 4 wins, among the first 4 matches, 1 loss has to be placed. That can be done in 4C 1 way or 4 ways. Here, out of 6 matches, 4 are won by India, 2 are won by South Africa. So, and also the last match has to be won by India. So, among the first 5 matches, 2 matches have to be won by South Africa. That can be accomplished in 5C 2 ways or 10 ways. Finally, out of 7 matches, India wins 4, South Africa wins 3, but India wins the last match. So, in how many ways can that be accomplished? 6C 3 ways or 20 ways. Altogether, we get 1 plus 4 plus 10 plus 20 or 35 ways. This is perfectly all right, except this only takes into account the number of ways in which India can win the series. The question was, in how many ways the series can be won? India can win it in 35 ways, and if India can win it in 35 ways, South Africa can also win it in 35 ways. Altogether, in how many ways can the series be won? It can be won in 70 different ways. Okay. Next question. The following figure shows the clay target in a shooting competition. All the discs in column A are red, in column B are black, column C are green, and column D are white. To win the competition, a shooter must break all 10 of these targets using pistol and only 10 bullets. You don't have more bullets than number of targets. And in doing so, he must always break an existing target at the bottom of the column. Okay. In how many different orders can the shooter break these 10 targets? Okay. Before we move any further, I'm going to do this. This is A1, this is A2, this is A3, this is A4, this is B1, this is B2, this is B3, this is C1, this is C2, and this is D1. Now see, the shooter can break these 10 targets, standard, these 10 targets in 10 factorial ways. Any order. But in order to, but he has to ensure that these four come in the order. A4 has to come earlier than A3, has to come earlier than A2, has to come earlier than A1. So these four can only come in a specified order. But right now, within these 10 factorial, these four can come at any place. So we have an overcount. In order to adjust that overcount, we have to divide it by 4 factorial. Similarly for B, B1, B2, B3. In this 10 factorial, they can come at any place. But I need it to be in a precise order. It has to be B3, B2, B1. So there is an overcount. In order to adjust that overcount, we have to divide it by 3 factorial. Same thing with C. We have to divide it by 2 factorial. We don't have to worry about it because it is a singular target. And this should give us our answer. Now, even when you're solving for this, 10 into 9 into 8 into 7 into 6 into 5, pi, 6 into 2. This should be our answer. 4 factorial will get cancelled and 3 factorial is 6. So this gives me 6 gone with 6 and 2 gone with 4. So I get 36 into 35. 36 into 35 into 10. Now 36 into 36 is 1296. So 36 less of that is 1260 into 10. Final answer will be 1260. The final answer to the question will be 12600. Okay. Next, in how many ways can 3 numbers be selected from a set of 43 consecutive natural numbers such that their sum will be a multiple of 3? Okay. Now see, these 43 consecutive natural numbers, the numbers within this range will be either of the type 3n or 3n plus 1 or 3n plus 2. Numbers that are divisible by 3, numbers that are not divisible by 3, numbers that leave a remainder of 1 upon division by 3, numbers that leave a remainder of 2 upon division by 3. Instead of 43 numbers, had there been 42 numbers, we would have said there are 14 numbers of each of these 3 types because they are precisely evenly distributed. But now that there is a 43, how does that change our mind? How does that change our mind? We could potentially have either 15 numbers, 14 numbers, 14 numbers. Either this is the distribution, or we have a distribution of 14, 15, 14, or we have a distribution of 14, 14, 15. These 3 distributions we can have. Let's see. For this case, let's just see for this case, first case, in how many ways can we select 3 numbers? In how many ways can we select 3 numbers such that their sum is a multiple of 3? If I'm selecting all 3n kind of numbers, that can be done in 15C 3 ways. Or if I'm selecting all 3n plus 1 kind of numbers, that can be done in 14C 3 ways. If I'm selecting all 3n plus 2 kind of numbers, that can be done in 14C 3 ways. Or if I'm selecting one number of each type, if I select one number of each type, even then I will get a multiple of 3. So 15 into 14 into 14. This will be the answer if I'm looking at the first case. But then when you come to the second case, realize the calculation will be precisely the same. If all 3 numbers are of the type 3n, we'll have 14C3. If all 3 numbers are of the type 3n plus 1, the calculation will be, plus 15C3. If all three numbers are of the type 3n plus 2, it will be 14C3 plus 14 into 15 into 14. This takes us here. This takes us here. Can you see mathematically both of them are identical? Mathematically both of them are identical. If mathematically both of them are indeed identical, then of course we don't need to worry about whether there were 15 iterations of 3n or 15 iterations of 3n plus 1 or 15 iterations of 3n plus 2. Either of these will give me the answer. Which tells me the answer is definitely determinable. An expression is getting created. Answer is definitely determinable. Now look at this. 15 into 14 is 210. 210 into 14. The answer will be greater than 2000. The answer will be greater than 2000. Among the available options, this is lower than 2000. This is lower than 2000. This is ruled out because it is definitely determinable. The answer marking that should happen right away at 4123. Now, if you want to precisely calculate it, even that can be done. 14 into 13 into 12 by 2 plus 15 not 2 by 6. 15 into 14 into 13 by 6. I can go ahead and multiply this by 2 because 14C3 and 14C3. This gives me, and finally 14 into 15, 210, 21 into 14. I will do the maths. I have a calculator. Why am I trying to do too much? This is 2940. And here I will have 14 into 13 into 2. Again, 728 I'm guessing. 28 into 26. This is 726. And here I will get 455. 728 plus 455 plus 2940 will get us to 4123. But I'm extremely surprised. I've written 726, but it should have been 728. 728, 455, and 2940. Okay. Why I was surprised was 6 plus 5 should give me a unit digit of 1, but I'm getting a unit digit of 3, which tells me there was something wrong. Regardless, the answer you will reach 4123, but you did not need to do all this calculation. You could simply have identified this product is greater than 2000. All these options, there is only one option that is greater than 2000. That has to be the answer. Next question. In how many ways can a maximum of 2 fruits be chosen out of 3 apples and 2 oranges and 2 mangoes and 1 peach? See, it says maximum of 2 fruits. So one acceptable selection is 0 fruits. And that can be done in one way. You don't select any fruit at all. Another case is when you select one fruit. The one fruit can either be apple or orange or mango or peach. So that can be done in 4 ways. Now, when you have 2 fruits, there are cases. The first case is both same and 2 different. If both of them are same, you can have apples or oranges or mangoes. You cannot have a peach. You can have apples or oranges or mangoes. This can be done in 3 ways. And when the 2 are different, which 2 fruits are you picking up? Out of apples, oranges, mangoes, and peach, which 2 fruits are you picking up? That can be done in 2 ways or 6 ways. So we have 6 plus 3, 9. 9 plus 1, 10. 10 plus 4, 14. The answer to the question will be 14 ways. Okay. Next, in how many ways can 4 boys and 4 girls be made to sit around a circular table if no 2 boys sit adjacent to each other? Okay. First, let us get all the girls to sit around this table. 4 girls around this table. They can be rearranged in 4 minus 1, 3 factorial ways. Girls can sit around the table in 3 factorial ways. And now, let's see This is the girl spot, this is the girl spot, this is the girl spot, and this is the girl spot. Now, spot left for boys is these are these. Spot left for boys are these spots between the girls because we had to ensure no two boys sit adjacent to each other. There are four spots, there are four boys. They can be rearranged in 4 factorial ways. And that's it. We don't have to worry about anything else. 3 factorial into 4 factorial is 6 into 24. Or the answer to the question is 44. Okay. Next. 15 students are sitting on a circular chair. Okay. Shouldn't be chair, it should be a circular table. Okay. Every student sings a song with every other student except the adjacent ones. Each song is of 2 minutes. How long will this chorus be if there is no time gap between the songs of any two pairs? Between the songs of 2 pairs. Okay. Let's pick up student 1. Student 1 is adjacent to student 2 and adjacent to student 15. So these two are out for him. And he's of course not singing a song with himself either. So for student 1, these 3 are useless students. With everyone else, he will sing a song. So student 1 will sing songs with 12 other people. And student 1 is not more special than anyone else. Student 1 is as special as every other student. If student 1 will sing with 12 other people, student 2 will sing with 12 other people. Student 3 will sing with 12 other people. All the way up until student 15 will sing with 12 other people. So, if you add these up, you will get 12 into 15, 180. But there is a problem here. Remember, in the pairings made for student 1, you had the pairing with S3 also. And in the pairings made with S3, you had the pairing with S1 also. Right now, all the pairs, S1, S3, S1, S4, S1, S5, all the pairs have been counted twice. So in order to get the precise number of pairs, you need to divide this by 2 to get the 90. There are 90 pairs of students that will sing with each other. And we were told each song is of 2 minutes. So the total time taken will be 90 into 2, which is equal to 180 minutes. Now, if you can perhaps, this is like a bonus idea, if you can understand this question is a geometry question, wherein they're asking how many diagonals are there in a 15-sided polygon. How many diagonals are there in a 15-sided polygon? Hopefully you'll remember it will be 15C2 minus 15, which is equal to 90, or 15 into 12 by 2, which is equal to 90. And then of course you multiply these numbers by 2. The question where you are avoiding your neighbors on a circular table and you are avoiding your neighbors in some activity, and the number of diagonals that you have for a polygon, they are pretty much the identical thought process. If you get it, great. If you don't get it, perhaps some sort of revision is needed. Next question. In how many ways can 10 persons be seated around a rectangular table with 10 chairs arranged as shown in the figure below? Okay. Whenever you have a non-conventional shape in which people have to be seated, first thing you do is, how many options does the first guy have? And the first guy walks in and sees this table, he will see that this seat and this seat are identical in nature. To its right, you have the small corner. To its right, you have the small corner. To its left, you have one seat. To its left, you have one seat. To its right, you have three edge with 3 seats. To its right, you have an edge with 3 seats. To its left, you have an edge with 3 seats. To its left, you have an edge with 3 seats. These 2 seats are identical. Similarly, these 2 seats are identical. These 2 seats are identical. These 2 seats are identical. And finally, these 2 seats are identical. When the first guy walks in, he sees these chairs and he realizes 5 of these chairs, there are 5 options available for him. There are 5 options available for him. He can select his seat in 5 ways. As soon as the first person sits down, with respect to that person, all the seats have become distinct. All the seats are distinct from each other. When the first person walks in, there is only relation defined in terms of seats with each other. Now that the first person has sat down, all seats have become distinct. 9 people are left. 9 seats are there. In how many ways can they sit? It will be 9 factorial, or the answer to the question is, of course, option A. Next question. How many different heights can be achieved by arranging 10 identical cuboids having dimensions 5 into 3 into 2 on the top of each other? Okay. Now see, there are 10 identical cuboids with these dimensions. So the minimum height attained will be if all of them are lying with a height of 2. So minimum height is of course 20. And the maximum height will of course be 50. Minimum height is 20, maximum height is 50. So within this range, we got 31 values. Now, all you have to be careful of, mindful of, and is basically identifying is within this range of 31 values, is there some value that cannot be attained? And good spots where values cannot be attained is towards the boundaries. Always check for boundaries. Can 20 be made? Yes. With 10 20s. Can 21 be made? Yes. 9 into 2 plus 1 into 3. 21 is made. Great. Can 22 be made? Let's see. 9 into, sorry. I need 22, no? So 8 into 2 plus 2 into 3. Great. 22 can be made. And can you see? From here, all the way up until 30, there is not going to be a problem. The final case will be 10 into 3 and 0 into 2. Up until 30, everything can be made. Now the challenge, if you want to go down this path, then the challenge will be for 31 also, 32 also. Let's see, for 31, can I need one more. So I'm going 1 into 2 plus 8 into 3 plus 1 into 5. Is this enough? 8 into 3 is 24, 1 into 2 is 2, and 1 into 5 is 7. How I'm breaking this down is, see, I know A plus B plus C is 10, and 2A plus 3B plus 5C. I'm seeing what all values can I take. Up until 30, this was the situation. Now, if I move one person from here to here, the total goes up by 2. But I want my total to only go up by 1. So I will shift one person here. So the next case generated is 1, 8, and 1. 2 into 1, 3 into 8, and 5 into 1, which gives us 31. Now, this gives me 30. This gives me 31. Can I come to 32 now? Can I come to 32 now? Can I come to 32? Very easily, this one that had 1 from B to A, shift it back. 32 will be 0, 9, and 1. Very nicely. Now again, if I want to go to 33, I will shift 1 from here and 1 from here. So this will turn 7, this will turn 2, this will turn 1. 2 plus 21 plus 10, 2 plus 21 plus 10. All of this is fine. I can get to 33 also. Let's say if I want to go to 34, again 0, 8, and 2. I can keep on going. I can keep on going. Is this fine? Yes, 34. All of this is fine. Next time, 35. You can generate a process itself. 6, 3, 1, 7, 3, 5, 4, 1. This is for 36. This is for 37. For 38, I will have how much? 6 and 4. 39, 1, 4, and 5. It's fine. Wait. 39 is 25 plus 12 plus 2. Yes, 39 is done. Let me continue here. 2A plus 3B plus 5C. For 40, again we will have 5 and 5, 0. This also gives us 40. Now for 41, so on and so forth. 42, 43, 44, 45, 46, 47, 48, 49, and 50. For 50, we know it will be 10, 0, 0. 50 is easiest to do. Let us also make the check for 41. 0, 5, 5. Now 3, 6, 1. 0, 4, 6. Yes. 2, 1, 7. 0, 3, 7. Red. 1, 1, 8, 0, 2, 8, 0, 1, 9, 0, 1, 9. And now we have finally found our problem area. Can you create a 49 in some way? There is no mechanism by which you can create 49. There is no mechanism by which you can create 49 because now see, there is no movement from 3 to 5 and 2 possible. You cannot create 49 at all. So from 20 to 50, there are 31 values. But from within these 31 values, 49 is not possible. One value goes away. Or how many different heights can be achieved? 30 different heights can be achieved. Of course, the expectation is not you will go through this entire process and check out every possible height in this range. I've done it just to show you how case generation can be done. Ideally, what you should be doing is looking at the first 4 values in this range and the last 4 values in this range. The first 4 values are 20, 21, 22, 23. Can these be achieved? You can see every time a 2 switches to a 3, it increases by 1. So yes, this can very easily be achieved. This is no problem at all. Then you check 50, 49, 48, 47. Can I get a 50? Yes. Can I get a 49? Problematic. Can I get a 48? 9 into 5 plus 3 into 1. And 47. 9 into 5 plus 2 into 1. Yes, this can be achieved. This can be achieved. Let me spend more time thinking about can I get a 49? No, getting a 49 is impossible. Okay, so this is the only number that is impossible within this range. So from 20 to 50, this is the unacceptable number and you mark 30 as the answer. This is how the exam solving should be. This processing of switching one number here and switching another number here and then bringing it back, all that was simply to show you how counting can be done. But in order to solve it in the exam, the process is much smaller. Okay, next question. There are 8 straight lines in a plane, no 2 of which are parallel and no 3 passes through the same point. If the points of intersections of these lines are joined, what would be the maximum number of quadrilaterals that can be formed? Okay. First thing you have to look at is 8 points, no 2 of which are parallel and no 3 pass through the same point. So how many points of intersection will be there? 8C2, which is equal to 8 into 7 by 2, which is equal to 28. There will be 28 points of intersection. And in order to make a quadrilateral, how many points do I need? 4. So how many quadrilaterals can be formed? 28C4, or option A is the right answer. That is all that the question demands. Next question. The diagonals of a convex hexagon intersect at n distinct points inside the hexagon. What is the maximum value n can take? Okay. Let's try and make a hexagon. Usually we have the habit of making a regular hexagon. You don't have to make a regular hexagon here because in a regular hexagon, hopefully you remember, a lot of times the intersection points coincide. But given that I'm looking for maximum value of number of distinct intersection points, let us make a non-regular hexagon. I've made a non-regular hexagon. Let me now make all the diagonals. 1, 2, and 3. Oh, 1, 2, 3. I have made a pentagon. In my attempt to make a non-regular hexagon, I've ended up making a pentagon. 1, 2, 3, 4. One, two, and 3. 1, 2, and 3. 2 is already made. And 3. And finally, and 3. Regular hexagon has 6 into 3 by 2. 9 diagonals. Do I have 9 diagonals? 1, 2, 3. 1, 2, 3. And 1. Yes. And 9 diagonals here, no problem at all. From every vertex, 3 diagonals had to originate. That is happening. So it is fine. Let us count the number of intersection points also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the answer to the question is 15. This is a very brute force way of arriving at the answer. Simply draw a non-regular hexagon. Draw, you will get your answer. Now, if you wanted to do it technically, slightly technically, then perhaps what would work is, where do I get this? That's stroke laser. Here, what I would prefer you to do is, remember in a hexagon, there are 2 types of diagonals. This long diagonal and short diagonal. Just from here, long diagonal and short diagonal. This long diagonal will be cut by this. This long diagonal will also be cut by let's say this is the long diagonal. 2 vertices on the left, 2 vertices on the right. This long diagonal will be cut here, will be cut here, will be cut here, and will be cut here. Look at the number of intersections on the long diagonal. 4 points, long diagonal. Okay. Let me in fact make this a red line so that the viewing is easier. Red line, these are the. Now for the short diagonal, let's say this short diagonal, at how many points will it get cut? Can I say here, here, it seems like only 2. This is this point. There is also one other point it will get cut at. Here, the long diagonal gets cut at 4 points. The short diagonal always gets cut at 3 points. So, how many long diagonals are there? There are 1, 2, and 3. 3 long diagonals cut at 4 points each, plus 6 short diagonals cut at 3 points each. How many intersection points are we getting? We're getting 12 from here, we are getting 18 from here. But remember, these points are being counted twice. Once when they are on the short diagonal, once when they are on the long diagonal. So every point has been counted twice right now. This 30 is not the number of intersections. This 30 is twice the number of intersections. So in order to arrive at the answer, you do 30 by 2, which is 15. Now this is complex and difficult to imagine and execute. And therefore, maybe the brute force way is the better one, wherein you can simply draw the diagram and arrive at your answer without having to trouble your brain too much. Okay. Next question. What is the total number of ways of selecting 20 balls from an infinite number of blue, green, and yellow balls if each ball of the same color are identical? So blue plus green plus yellow is equal to 20. Now, all you have to do is you have to select some 20 balls in some way, some distribution. We have infinite number of balls. So, think of it this way. I have 20 chocolates to be distributed to 3 friends. And these 20 chocolates are kept in a row. So, I have 20 chocolates and 2 partitions. I have 20 chocolates and 2 partitions. And any time I take these 22 objects and rearrange them in any way, I will get a new way of distributing it among people. So that can be accomplished in 22 factorial by 20 factorial by 2 factorial. Essentially, what I'm using is n plus 1 c r plus 1. ऐसा कुछ होता है ना? N plus 1 c r plus 1. What is popularly known as non-negative integral solution sets. I think non-negative integral solution sets. But what I'm essentially doing is I have 20 chocolates, 2 partitions. These 22 items can be rearranged in 22 factorial ways. Of these, 20 are identical and 2 are identical. So we divide it by that. And this should lead us to our answer. So we get to 22 into 21 by 2. Which is 11. 11 into 21 is equal to 231. Or the correct answer is option C. Next one then. Find the total number of terms in the expansion of A plus B plus C plus D plus E is equal to 20. Okay. Fairly straightforward again. Now see, whenever you expand a bracket, the power that you have always adds up to 20 only. So some generic term will have A raised to the power E into B raised to the power Q into C raised to the power R into D raised to the power S into E raised to the power T. This would be some generic term, and these powers will add up to 20. So we have P plus Q plus R plus S plus T is equal to 20. Again, 20 chocolates, 4 partitions. In how many ways can this be accomplished? It can be done in 24 4 ways, if you know the idea behind it. Otherwise, I have 24 factorial by 20 chocolates being identical and 4 partitions being identical, which will lead you to 24C4. Why I'm not calculating it further? Because the options are given in such a manner. You'll mark option C, and that is the entirety of this video. Hopefully you learned something, some ideas clicked in your head. See you again next week.